Now I want to cover the second point, or the second half of this lecture. I want to talk about stationarity. And this is one of the very important, if not the most important, thing to look at, or to check in your data since you deal with time series data. So it's very important to check the properties of your data. So as a general definition, what that means, stationarity means, first we need to think of what a time series is. So a time series is an example of a stochastic process, which means it's a sequence of random variables ordered in time. And the main issue here is that when we run regression on time series, the regression this assumes that these time series are stationary, which means they have constant mean, constant variance, and the covariance depends only on the distance between two periods, not on time itself. So if a time series satisfies these conditions, so it is called weakly stationary, okay, and this is something we shouldn't worry about if that's the case. But in reality, this is not the case. So with most time series data you deal with, this is not, these assumptions or these properties are not true with most economic and financial time series. Okay, so again, so in regression we assume it is stationary, but the case, or the real case, is not. It's not stationary. What do you mean by stationary? Again, these three conditions. Remember, the constant mean, constant variance, and the covariance depends only on the distance between two periods, not on time. And the problem is that these conditions, or these are not true in most of economic and financial series, and that's why they're called non-stationary. Okay, so most of the series you will be dealing with will be, so the normal is to be non-stationary. Some of them will be stationary in level, that's fine, but what I'm saying here is that in general, the majority of the time series data we'll deal with are likely to be non-stationary. So what's the problem? Okay, we said when we run regression on a time series data, we assume stationarity. So what if the data are not stationary? What if we run regression and the data is not stationary? So what's the problem here? Well, the main problem here is that you are likely to have, you could have what we call a spurious regression, or a regression that is not meaningful. Meaning, you could have run a regression between two variables that has no relationship at all. They're not correlated at all. Okay, and your regression give you amazing results. There's statistically significant relationship between both variables. Wow, and you jump and say, oh, that's impressive. I found it, and now I figure out why, or what the main reason of growth, for example, in country X. So if you run a regression between maybe your height over years and GDP of your country, you might find significant relationship. But does that make sense? So as you go taller, your country economic growth, no, it doesn't. It's not. They're not related. It just doesn't make sense. Okay, that's what we mean by spurious regression. So you have a strong relationship, statistically proven. You see it, but between two variables that they are not related at all. Okay, and there's no way they are related, and I'll show you an example now. Okay, so there's one of these silly examples. I think there's I could send you the link to a large number of many number of examples of researchers actually did that. They collected data just for fun, yeah. They collected data between variables that there's no way they are correlated. There's no relationship between them. Okay, like infant mortality rate in X country and GDP growth in another country. Something like unbelievable. Like you can see, like you see, and they are, oh wow, they're statistically related. No, it's not. It's just because both variables have upward trend or downward trend, so they change over time, and this is why the regression gives you some sort of correlation between correlation between both. Okay, it's just because of the nature of this series. Both series move upward or downwards. They have some trend over time. Your height change over time, and growth change over time. Okay, so this doesn't make them related in any way, anyhow or any way. I don't know why, but anyway. So in that case, you could have a statistically significant coefficient, high R-squared, very impressive results between two variables that they no way are correlated. So this is just to show you an example. So I tried to create some data, and to do this, I just I'll show you the code how to create this data. I followed like an AR process, which means YT depends on YT minus 1, and row here if, so this is AR1, meaning I just want only one lag, YT minus 1, and some random error. And then I created some data here. These are artificially generated, okay? So these are not real data. Just to show you the difference between a stationary series and you see non-stationary series. You see this have like upward trend. This is not stationary. This is not stationary. So this sort of time, you see, it's going up and down around the same mean, so constant mean, and kind of the way it's spread around that mean seems to be equal. Okay, so it seems to be more stationary data. But most series you will deal with will look like this, all this. Okay? So this one, you see, just going up and down around the constant mean, and the variance, or how much they spread around that mean, seems to be equal. So going to the idea of the spurious regression, I created another variable, generated another variable, two random variables. These has nothing to do with each other. I just plot them. And here's the scatter plot of both variables. And guess what? I'm going to run regression between these two. Wow, statistically significant. You see the coefficient, the estimated coefficient? X has statistically significant relationship with Y. So I created the variable, and I know they have nothing to do with each other. They're not correlated at all. Okay? It's just the way they evolve over time, the series itself. It seems they are, but they are not. Okay? It's just the way they change over time. Okay? But they have nothing to do with each other. Okay? So these are uncorrelated. They should have no relationship, even though when you run a regression between two variables that they are not correlated at all, because they are non-stationary, they are not stationary data series. That's why you see there is a significant relationship between X and Y, and it's highly significant. Okay, so it's very highly significant, which is not true. We know that it's not true. Okay, so this is the idea here. So again, just before jumping to the next point. Okay, so first, we assume stationarity, or regression assume that the series are stationary. And what that means? Constant mean, constant variance, and the covariance depend on the distance between 2 points, not in time. Okay? So, in reality, most time series data you'll deal with are non-stationary. I didn't say all, but at least most of them will be non-stationary. Okay, so what is the problem? The main problem here is the spurious regression, or the regression that is not meaningful, or meaningless regression that doesn't mean anything. Okay, remember the example about your height and growth rate. Okay, don't know how you can relate these to each other, but in human regression model, you might find a significant relationship between both. The example we show here, we just generated data that are not related for two series, and then and then we find significant relationships. So that's an example of spurious regression. So now, how do we know that a series is, whether the series is stationary or not? Okay, you could plot the series and look at the series whether it has trend. Does it look like very stationary, like the first one is very straightforward? But in all cases, in time series data or any regression, you should know your data. You should look at the descriptive statistics or the summary statistics. You should plot your data. That's like ABC regression or dealing with data anyway. But in addition to that, you need to test, formally test whether you have your data is stationary or not. And the test that does that is a Dickey-Fuller test. And the test is very simple. You have YT depends on rho, YT minus 1 plus some error. And the null hypothesis here that the data is not stationary or has a unit root, meaning that this row equal 1. So if this row equal 1, okay, that means the data isn't stationary. The data has what we call a unit root. If row is less than 1, that means the data is, your series is stationary. For the test purposes, actually it looks at the change rather than YT, so it's change in YT. Okay, so this comes from this one by just say YT minus 1, and then that can take you to this form. In this case, you have 3 forms of the test. The first one, which we call the random walk form. The second one is a random walk with drift. You have this alpha. And the other one, you have it with deterministic trend. So you still have with drift, and so with alpha and with T. T here is the trend. Okay? So you have 3 forms of the test. And when you run the test, you need to specify which form you're looking at. The only difference is the critical value, because they all have the same null hypothesis and the same alternative hypothesis. In this case, because we transform this to this equation, not this one, because we have here delta YT, not YT. So that means gamma here, which is this coefficient, equals 0. That means the data is not stationary, or it has unit roots. If gamma is less than 1, this is the alternative, and that means the data is, or your series is stationary. Okay? So, as I said, this is exactly what I said. So if you reject the null hypothesis, that means your data is stationary. If you fail to reject the null hypothesis, that means your data is not stationary. The difference here that this test doesn't follow T distribution or T test, so you can't run this regression. You do actually run this regression using OLS, that's fine, but you can't do the T test based on the T distribution. So what you have here, you take the test statistic, and then you compare this with critical values that are produced by simulations that are provided by Dickey-Fuller, and they call this statistic or this test tau test, and they provide their own critical values. And most softwares give you these critical values, so you don't have really to worry about how to generate or how to obtain these critical values. So the idea here, okay, in the usual way, so if you have the computed tau or T greater than in absolute value, so greater than the critical value, then you reject the null hypothesis. What is the null hypothesis? What's the null hypothesis in Dickey-Fuller test? Yeah, so which means it's not stationary. Yes, okay. So, so you reject this null hypothesis if the computed statistic are greater than the critical value, or if you have a very small p-value, smaller than the significance level, let's say of 5% or 1%. So if you have a smaller value, then you reject the null hypothesis, and that means, again, non-stationary series. And as I said, these three forms with random walk with drift, random walk with drift, and time trend, they all have the same null hypothesis, but they have different critical values. Okay, so but in all cases, as I said, most softwares, including R, they produce this for you, and also they produce the p-value, so you could just look at the p-value and decide based on the p-value provided. This is an example of the test. I did this on I think the US GDP data, if I remember. Yeah, well, it's US series anyway, but I think it's a growth rate. I'm not sure if that was the growth rate or the unemployment rate, but one of the two variables that we did. And as I said, this is the test statistic that's produced by R, and as usual, I'll record a video to show you how to reproduce all these tables and graphs and tests as well. But at the end, you could look at this. Okay, so if you fail to reject, that means that the data is not stationary. So your data has a U series here has unit root or non-stationary, because you cannot reject this. So if you fail to reject, that means the data is not stationary. And obviously, when you look at the data, it doesn't really look going up and down around a constant mean at all. It's actually having a kind of trend here. So so it's obviously it's not stationary. It's not stationary series. Okay. So you could actually, the augmented Dickey-Fuller test, add different lags or more lags. So if you look at the Dickey-Fuller test, what we have here, we have the change in yt, delta yt, and here we have only yt minus 1. So we have AR1 process, or we go back in time only one lag only in time. Okay, but with the augmented test, you could actually add. So this is the same. That's exactly the same test, the same equation, okay? But with the augmented Dickey-Fuller, we add more lagged value of the dependent variable, okay? So you could go back in time here, t minus t equal 1, so starting from 1 up to m. M here could be the maximum lag length of the dependent variable. Okay, so how do we deal with the stationarity? So let's now know, we knew now that this series is not stationary. We couldn't reject the null hypothesis, so it is not stationary. It has unit root. So, and we know if we use this series to do regression, we are worried about spurious regression or the regression that is not meaningful. So what should we do? Okay, one way you could make the series stationary, so a non-stationary series could be converted to a stationary series, okay? And there are ways to do that. One way is if we have a trend stationary, what we call the trend stationary. So if the series has, let's say, upward trend, okay? So it has a trend that seems non-stationary data or non-stationary series. However, it goes up and down around that trend. Okay, we could do what we call take out that trend, and that will transform the series to be stationary, which we call detrend the series. How? And in this case, the series actually is called trend stationary. So because it is stationary around that trend, so it goes up and down, not around its constant mean. It goes actually up and down around that upward trend. So if you detrend the data, if you take that trend away, if you filter the data, if you filter the trend, you take it out, then the result will be a stationary series. And that's exactly what it means, trend stationary. So in this case, trend stationary, so you have YT, and this is your trend. So it goes up and down around that trend. So if you run this regression and you obtain the residuals from here, these residuals will be your detrended series. So after taking out that trend, okay? So what is left here of your series, which is the hat here represent the residuals, that means these are your detrended data. And if your series is a trend stationary, that means once you detrend it, once you remove that trend away, then you get a stationary time series. How about what if your data is not a trend stationary? What if it is not going up around a trend? Okay. In that case, you could difference the data. So take the first difference or the second difference, depends how many times you go back. You have to difference the data, sorry. So if a series becomes stationary, so you could take the first difference and do the test again, or plot the data and do the test again. If that changed the data to be stationary, that means your data is integrated of order 1. Okay? So if they have a series that I need to difference once, so if I have a non-stationary series that I need to difference once to become stationary, that means the series is integrated of order 1, or it's called I1. If I have a series that I need to difference twice, so I took the first difference and then I differenced it again, and then it became only stationary after I differenced it twice, that means the data or the series is integrated of order 2. And so on. So it depends on if you difference d times, that means your data or your series is integrated of order d. And the good news is most of the series you will deal with, it's mainly I1. Okay? There are some rare cases of I2, but mostly will be I1, which means you difference it once, you take the first difference, and then that will convert the series into a stationary or a non-stationary series to a stationary series. How about if the series was in level stationary? That means it's integrated of order 0, because you don't need to difference it to make it stationary, because it is actually stationary. Okay? So if it was a stationary, if your series is stationary in level without any differencing, that means it's integrated of order 0 and it's a stationary series. So this is very important. As I said, with I0, with a stationary data, the series will fluctuate, so go up and down around a constant mean. So it's exactly that way. Look at the first graph here. This is exactly what it means. This is I0. This is a stationary series, so it's going up and down around a constant mean, and the variance, so the way how much it's spread around the mean seems to be constant. So so that's the idea. So that's why they call it mean reverting. So it goes away and come back, goes away and come back, goes up and down around the mean. That's why they call it mean reverting. But I1 or non-stationary data doesn't show that. It's like sometimes it has upward trend or downward trend. It doesn't really show this sort of behavior going up and down around. So as I said, most of non-stationary data, or most of economic data that are non-stationary, so they are I1. So so mostly you will have to difference it only once. In some rare cases, you have to do it twice to make it stationary. This series here, it was not stationary, and then and the p-value here was large, so we couldn't reject the null hypothesis. So when I difference this series, it becomes, you see, going up and down, kind of constant mean here. And I think I did and I did the test here, and then a small b value, you reject the null hypothesis. That means it became stationary. So you see this one is the differenced one. So I plot the series after I difference it, and now it looks, if you compare this to this one, so this is the series, this is the original one. So after I difference it, I obtain the new series, this one. And this one looks more stationary. Now it's going up and down around this constant mean. And when I did the test, the p-value is very small here, smaller than 5%. That means I reject the null hypothesis. So when you reject the null hypothesis with ADF test, that means your series is stationary. Okay? And that's what we wanted here to do here. Okay, so just to conclude the lecture, we covered some examples of dynamic models. We compared between stationary and non-stationary series. We know what are the implications or the consequences of dealing with stationary series, and how to convert a stationary series, a non-stationary series, into a stationary series. And then next time we'll talk about VAR and VEC model, vector autoregressive models, and error correction model.